Hello, everyone. I wanted to very quickly go over Project 4, since a few students were confused about what to do here. In this project, you're asked to design a sequence detector that detects a 12 bits binary number. The way you choose this number is based on your BSU ID, and it's gonna be the rightmost three integers. And it has to be like the ones on the right, because on the left, everyone almost have the same three digits. So this is just an example. Let's say that your rightmost three digits are 564. Then you need to represent the 564 as a binary coded decimal, BCD. This means that every integer will be represented by 4 bits as a binary number. So you'll put them together and you'll have a sequence of 12 bits. So you are designing a sequence detector that will detect when you get those 12 bits. And this must be bitwise input. I will explain what this means in a second. If you've taken ASIC before, this is similar to one of the projects in ASIC, but not exactly the same. So the sequence will be different for everyone, but you will have 12 bits eventually. Let's say 1100. This is just very randomly now. 1010 0011, for example. So that's your 12 bits. So you need to design a finite state machine to model the sequence detector. And um, the project has more complications later on, but for now, I recommend starting a very normal sequence detector. Let's say this is my reset state, S0. So this is S0. This is also my initial slash reset state. So this is where I start. Now, this is my sequence. I'm just gonna map my sequence into state machine. If I have one, let me copy this actually a few times. I'm not gonna solve this whole problem, but just to give you an idea about what to do. Um, so S0, S1, S2, S3, 4, 5, and so on. Uh, I'm not gonna number the last one, but I'm just gonna assume that this is the last state. So we're gonna map this. If I get one, then I move forward to the next one. So this is input one. If I get another one, I'm just reading those. If I get another one, I move to the next one. If I get zero, I move to the next one. If I get another zero, I move to the next one. If I get one, I'm talking about this one here, the first one, then I move forward to the next one, and so on. Until if you make it in the right sequence, you get the right perfect ones all along until you get to the last one. You will have some more states in between. I'm removing them for now, but you will be in this last state, and this last state will basically have like an output one. Output one means the sequence has been detected. I'm gonna make this just a little bit bigger. Every other state will have an output zero. So you will have some logic in your output logic for the state machine that will assign output zero to every one of them because we're checking every single cycle. Every one will have output zero except the last one, which only you can only reach this after having gone through the entire sequence, this sequence, your sequence. And after you get the correct sequence, we just keep going. This doesn't stop. This just goes on forever. So when you get the right sequence, if you get another input, it goes on. Now, this is an overlapping detector, meaning here, for example, if I get 1100, so 110, let's say I get 1 here and not 0. If I get 0, it's a correct sequence and I go back, I go to 4, right? What if I get 1 here? Because you can get either 0 or 1. Do we just go back to the reset state and wait for 1? Doesn't make sense because you already have 1 here. This branch has 1, right? So we'll go here, we'll assume we already have the first one. From here, this has 1. So we have 1, 1, 0, 0. We got the first 4 already. So this is overlapping. If you get the wrong sequence, every one of these will have either 0 or 1. For example, this one, you expect this to be, you expect this to be, if you get 1, you move on. If you get 0, you're just gonna wait here until you get 1. But if you get the wrong one, it might go back to the reset state, or it might go somewhere else. It's not gonna go forward, but this one, if you get 0 again, you're just gonna go back here. But it's not gonna be the same for all of them. So each one will have two possible outputs. It can be 0 or 1. You have to think about one of them will be the correct sequence, right? That's why you made that state. And one of them will be wrong. But if it's wrong, it doesn't just go to reset. It might go to reset, but it might not. It will go to the previous state that makes sense, that you already have a part of the sequence that was correct. So you're gonna design this. You can use Moore or Mealy. I recommend just using the simple sequence I'm showing you. Once you do this is the first part. The second part, I'm asking you to make a deadlock state. What does this mean here? So I'm giving you an example. It can be the input sequence 1, 1, 1, 1. This is just an example. You don't have to use 1, 1, 1. You can if you want, but you don't have to. And the FSM should not transition to any other state simulating a lockout condition for security. It's stuck forever. Even a reset cannot take it back. So you can make this 4 bits, like I recommended 4 bits, but it doesn't have to be 4 bits. You can make it as many bits as you want. I recommend just using 4 bits. It can be 1, 1, 1. If you already have 1, 1, 1 in your sequence, then you cannot use 1, 1, 1. You have to use something else, like 1, 0, 0, 1, for example. For here, I'm just going to make it 1, 1, 1, 1. So why do we have this? This is like a security feature. Let's just say this is like a PIN number for a bank account or anything. And you know that someone thinks you have those 4 bits initially. Someone thinks this is the first digit. So they will try this and they will fail because this is not actually correct. But then they will try again, right? If you don't do anything about it, they will just keep trying, trying, trying until they find until like they guess this number and get in. That's why we're designing this deadlock. We know they think this is a value. We know they will try it. Once they try it, we want them stuck forever. Not even a reset can take them back. You can never try again. I know you're trying to hack me. I know you're gonna try this. Once you try it once, you're stuck forever. So how do we do this? We're starting from the same reset state, right? My sequence here, this will be different for everyone. But my sequence here is 1, 1, 0, 0. So this could have 0, which is the right sequence. It could also have 1, right? It has, if someone gives it 1, then we're kind of branching out of our sequence. I'm branching out. I am gonna create uh, a state here, for example, that's, you can call it anything. I'm just gonna call it something like that. And this is 1. If I get another 1 here, then um, you have to call it something else. That's also 1. So now that's, oh, sorry, that will be 1. So now I have 1, 1, 1, 1. That's my deadlock state. If someone is here, I want you to be stuck here forever. Not even a reset can take you back. This should not be one of the states that goes back to reset. Whether this is 0 or 1, it's just going to be stuck here. You can never get out of here. Another state you have to design, and it's an isolation state for maintenance or something like that. It will also be 4 bits. It has to be different than the first 4 bits in your sequence. It also has to be different than the 4 bits used in the deadlock. You can call them anything, just something different. Let me copy this. Okay. Like maybe 0, 0, 0, 0. So you will do the same thing, like very similar to those 4. You start from here, you'll have 0, 0. It just make it another branch. Those will be branching of your circular sequence that goes on forever. If someone enters those 4, it's a very isolated state, except reset will take it back to the initial state. So the difference between the deadlock state is if you get to this state, it will be stuck forever. It cannot even be reset back. And if you get an isolation state, it's isolated, but it can be reset back. That's the entire difference. And just to give you an idea, like I designed this project trying to give things to VC Formal to kind of get mad on, or like for the automatic property extractor apps, AEB app, to find things out for you. It might still not work for the way you like make the sequence and the finite state machines, the way you design it, but that's okay. I'm just like trying to give you an idea of why I chose to include deadlock and isolation. And then stability, let's just go here. Additional check states. So let's say you have like 12 or 13 states and you made the design already. I'm asking you to include check states. What does this mean? So I'm gonna color this something different, maybe yellow, and I can make it like S0 check, right? That's the first one. So instead of going from 0 to 1, I want to check and make sure that this signal here, this transition here, is actually stable for 2 cycles, not just one, just to mitigate any noise that we could have. So I'm going to remove this one, which was 1, and I'm going to now require, I need to get 1 twice. 1, 1. What did I do here? I just broke the 1 here, that was just 1 transition into 2, and it goes to this check state. If I get 1, then I get 0, I'm just going to go back to the previous one. This is not overlapping. This part is not overlapping. If you get the wrong one, just go back to the previous one, the previous actual state. So you'll add a check state basically for each state or each two, like between two states in your diagram. So that's going to be like S1, this is going to be like S2. So I really recommend first designing the sequence and then just breaking, replacing. This could be 1 or 0, but here it's like 1 again. So I'm going to break it 1 here, then 1 here. And if I get 0, I'll go back to this one. Here, I'm going to break this 0 into 2 zeros. 0 and another 0. And so on. And if I get 1, I'm just going to go back to the previous one. So you're just going to do this for the whole design. And that last one is what you will code in System Verilog. So you will include actually those states. Okay. What else? The stability counter, you don't really need a counter here. Basically, this is the counter. I'm getting 1 twice. This is the first time, this is the second time. This is like your counter, but you don't need to actually include a counter variable in your design or test bench or anything like that. It's just like I'm getting 1 twice. You can make it 3 and require to like 1, another 1, another 1, but that's not needed. You don't actually need this. And then, yeah, so if the input changes before the counter reaches the threshold, so if the threshold is 2 here, I'm getting 1 twice, 1 and 1. If it changes, so I got 1, but it changed, it's not 1 anymore, then I'm just going back to the previous state. That's really all there is. So you will add, like, this is just an example, and this is like a very rough number. It might be more or less, like you might have 13, 14 states, depending on how you design it. You're detecting 12 bits. So that's why I said, for example, and you might have fewer check states because you're actually adding them between each 2 states. That's also fine. You make assumptions, you can make assumptions. It's fine, just make it clear which assumptions you're making, and you cannot make assumptions to like make the problem super easy and be like, I'm assuming that the clock cycle is 2 instead of 1, and then I don't need check states. I'm not going to accept this assumption. But you can make an assumption that the deadlock is 5 bits instead of 4. I can assume that, things like that. You can make assumptions. If something is not super clear, it's probably because I didn't want to confine it, that you're free to try something different as long as it's not conflicting with the requirements that's already given to you. And the check states are part of the requirements. So you're going to design the finite state machine, you're going to implement it in System Verilog like the final one once you have all the states. I'm asking you to add some things that might seem weird, like why are we making a case state with X, with don't care, again, and why using unique specifically. I'm trying to create things for BC formal to pick on. So when you actually use uh, FXB, it should find the don't cares. If you use AAB, it should also find something to do with the unique cases. If you don't get it, that's okay. Just comment on what's happening. If you get them, I'm asking you to comment on what's happening too. What else? Yeah, so it will find bugs. It will tell you where the bug is. I need you to fix them. Like, if you can't fix them, just explain why. So if you get that this X is a bug, this is a different task. This is not a design requirement. Okay, you're gonna remove the X, add something else, run it, clean it. If you cannot clear it, sometimes you might not be able to like fix it just because it's part of the design. You just need to comment why it cannot be fixed. Um, but the FBV, this is a formal property verification. You will need to write at least 15 assertions. And if you need to kind of explain if they don't pass, if they are failing, then something is wrong in your design. You need to go back and fix it or explain what do you think is happening. Again, sometimes you cannot easily fix it. It's fine. Just explain clearly what's happening. If you made a mistake implementing the design, then those properties should help you fix it. If you made a design meeting those requirements and for some reason one of your assertions is failing, and if it's clearly not because you broke one of the requirements, then it's fine. Just like try to explain what you think is happening and you should not lose any points. But if you already made something wrong and you ignored the assertions that told you that something is wrong, then you might lose some points. So the bulk of the work here really is making the state machine. Once you do this and code it in System Verilog, you're almost done. I know the project looks really big, but once you do this, this is automatic. You're gonna specify the app, just follow the tutorial. We just put those 4 tutorials. This is completely automatic. You will basically like copy the tickle script in the video or the tutorial and map it to your files, very similar to what you did in project 2 using the SIG app. And this one is also fully automatic. You don't really do anything. You just need to like modify the tickle script and run it and just put the results, fix any issues for both of those. This one is also like really automatic. It just gives you ideas into any unreachable states. And I'm not requiring anything specific here. I just want you to like, I think I'm asking you to run this after you already put your properties. And then you will run this one. FBV is where you will write at least 15 properties. And if you have any issues with that, please reach out to me. I can give you resources or help you how to write those properties. And then you're basically done. This is just an elaboration of what you need to do, what you need to test, um, why you're running this, or what are you like. I'm not expecting you to do anything here really. Just like run it, give me the screenshots of the percentages, any unreachable states. What did the report say? This report basically gives you an idea about what was covered in the formal analysis and what needs to be covered using another method, maybe by making the formal analysis more rigorous, adding more assertions, constraints, or just working with simulation to fix uncovered parts of the design. Okay, so that's basically the project. Um, please take your time to make your design, try to implement it, and if you run into any issues, please reach out to me. Thank you.